I'm Matt from Canada, and I'm here to talk about orbits. You probably already know what an orbit is, right? You probably also know the force responsible for orbits. Gravity. Right, the thing that keeps us stuck to the ground and makes objects fall to the earth. But if gravity causes orbits, why doesn't the moon come crashing into the earth?
Okay, picture this. You throw a ball horizontally, parallel to the ground. What happens? As you expect, the ball falls to the ground with the acceleration due to gravity, 9.8 meters per second squared. But what if you were able to throw the ball so fast that by the time it hit the ground, the earth wasn't there? For simplicity, let's pretend you were standing on something, a rock for example, so that you were releasing the ball from 4.9 meters above the ground. If you were to drop the ball from this height, it would take 1 second for it to reach the ground, due to the acceleration of gravity. Now let's pretend you have a mechanical super robot arm that allows you to throw the ball at any speed you'd like. With the radius of the Earth being 6.4 times 10 to the 6 meters, in order to keep the ball 4.9 meters above the ground, we would have to throw the ball at a speed of 7,919.6 meters a second. At this speed, by the time the ball reaches the ground, the Earth has curved away. What would happen next? Would the ball keep falling? Yes, in a sense. An important point we have to remember is that the acceleration of gravity is always directed towards the center of the Earth. This type of acceleration is called centripetal acceleration. Since the ball is still 4.9 meters above the ground, it will follow the same path along the side of the Earth. Provided it maintains its velocity, the ball will continue to follow this path all the way around the Earth until it reaches the top again. Because the ball is traveling at the same speed and is the same height above the surface of the Earth as it originally started with, it will repeat the entire motion indefinitely. We can now say the ball is in orbit. We can see that the ball is still affected by gravity in the same way as usual, but it is traveling so fast that it essentially misses the Earth every time it falls. The ball is always falling and it will never stop, unless its velocity is changed. If a ball was in orbit at 4.9 meters above the ground, it would take 1 hour, 24 minutes, 37.58 seconds for it to return to its original position, giving you plenty of time to duck. Of course, even if we were able to launch a ball at such a high speed, it would be impossible to create an orbit at such a low altitude. There are way too many trees, mountains, and air particles in the way. But in outer space, there are no obstacles or gas particles to cause drag or reduce the speed of the object. Therefore, objects like satellites and the International Space Station are able to maintain their speed and stay in orbit around the Earth. That's right, the ISS is constantly falling around the Earth, staying the same distance above the surface as it travels around.
This also helps explain the phenomenon of weightlessness, or zero gravity, that people experience when orbiting around the Earth. The constant free fall gives the illusion of the absence of gravity, like a drop tower at the amusement park, even though they are still within the Earth's gravitational pull. Knowing how orbits work is great, but this doesn't answer our question about large celestial bodies like moons and planets. Nobody launched the moon around the Earth at a predetermined speed, or set up the orbits of the solar system around the sun. So why do these orbits occur?
Scientists believe that the solar system was formed when a giant cloud of gas and dust was compressed by the explosion of a nearby star, which is called a supernova. This caused the cloud to spin faster and faster. The hottest, most massive material in the center of the cloud became a star, the sun, and smaller bodies spinning around the center fell into orbits around it, based on their mass and velocity. Only objects traveling at a speed in perfect balance with the gravitational pull of the sun entered orbit. Objects traveling too slow were pulled right into the sun, while objects traveling too fast flew off into the depths of space. A similar process occurred in the case of moons, except around their respective planets rather than the sun. Today's planets, and the moons of these planets, are all in perfect balance. In all, an orbit is the periodic path taken by an object traveling around another object due to the central object's gravitational pull. The traveling object has a velocity that counteracts this gravitational force and allows it to remain the same distance above the surface of the central object. So the next time you see the moon, you can think of it as a giant tennis ball traveling around the planet, always falling but missing the ground. And that's a very good thing, too, for if the moon was falling towards the Earth might have a serious problem.
Oh, no way! Ah!